Hey everyone, welcome back to physics. This will be lecture 13 of the course. And in this section, we're going to dig in a little deeper on Newton's first law and work an example or two that takes into account Newton's first law of motion. So let's go ahead and jump into it. Call this section 3.2, Newton's first law. Okay, now in the previous lecture we stated Newton's law and talked about it briefly. Let's spend a little more time on it here. So what does Newton's first law say? Well, it says that objects in motion/rest tend to remain in motion/rest unless acted upon by an outside force. Okay, so this is what we saw last time. Objects in motion tend to remain in motion. Objects at rest tend to remain at rest unless they're acted upon by an outside force. I think last time we said, hey, maybe we should use the word net force, unless acted upon by a net force. And I think really the whole statement could be restated slightly and possibly be, while maybe slightly less conversational, a little bit more precise, and would tend to draw out some of the more important aspects. So let's instead say a body acted upon by no net force moves with constant velocity. Okay. Right, and of course, when we say moves with constant velocity, that's kind of loaded up, right? That means, first of all, that the velocity can be zero, i.e. the object can be at rest. Also, it also means implicitly constant velocity implies zero acceleration, so the acceleration is zero. So a body acted upon by no net force moves with constant velocity. Velocity could equal zero, but acceleration certainly equals zero. Right, and so this is possibly better as a statement because it highlights the no net force part of the expression, a part of the law. The key to the first law, in my opinion, really is the quote unquote no net force part. Right, so I'd say the key to the first law is the no net force part. Okay, let's think about a couple of examples. We've certainly seen this. You got a ball resting on a surface. Gravity is pulling the ball down, and the normal force is holding the ball up. Because the ball is at rest, Newton's first law tells us that the sum of the forces at work on it must equal zero. So because the ball is at rest, Newton's first law tells us that essentially the normal force in this case, the magnitude of the normal force and the direction of the normal force, is equal to mg. Right, and so we can use Newton's first law frequently use it to tell us something about the equation that we're interested in setting up. Right, if the object is at rest, then it tells us that all the forces acting together must equal zero. Right, now and critically, this is true also in the case where velocity is non-zero but acceleration is zero. Right, so consider another example. This time let's think about like a hockey puck on like an air hockey table. Right, so you've got, again, your mg, you've got the normal force acting as well. Right, and at least let's just say that the hockey puck, so imagine a hockey puck sliding with constant velocity on a surface, probably like an ice skating surface or whatever. But so imagine a hockey puck sliding with constant velocity on a surface. Now we know just from thinking about the problem that you're obviously going to have gravity pulling it down, normal force holding it up, and you're going to have, because the puck is sliding against the surface, you're going to have kinetic friction. Right, so you're going to have this friction force. Now, critically, when we read it and it says that it's sliding with constant velocity is going to imply something here, right? Because of Newton's first law. There's no force acting contrary to friction. So the fact that it's not slowing down, coupled with what we know about Newton's first law, tells us something about the kinetic friction. So Newton's first law implies that in this case the kinetic friction force must be equal to 0. Okay, so it's 0. The acceleration is 0 because of the constant velocity. Okay, and so Newton's first law tells us that the kinetic friction is equal to 0, and therefore the surface is frictionless. Okay, and so a lot of times Newton's first law is going to come into play in that it's going to allow us to kind of frame up the problem. If you remember back to like 1D and 2D kinematics, a lot of the challenge of those type of problems that would come up in those spaces was just knowing how to ask the question of the equations. And Newton's first law gives us a crucial tool in that in our problem solving, in that it allows us to equate all of the forces equal to 0 oftentimes if the velocity is constant, right? So it's a great tool for problem solving. It's also just the way the world works too. It's so it's not just for solving problems, it's also critically how the world works. Now, something that we'll talk about in more detail further on, but I do want to mention it and underscore it a little bit, is this important related concept. Whenever you talk about the first law, there's this concept of inertia that is kind of embedded in the law. So remember, the law says a body acted upon by no net force moves with constant velocity. Maybe the first expression is better. A body at rest tends to remain at rest, and a body in motion tends to remain in motion. The idea being that if a body is moving, then it wants to stay moving. And if a body's at rest, it wants to stay at rest. And this brings into focus the idea of inertia. Now, inertia is, you can think of inertia is the property, it's a property of matter that causes matter to resist changes in its motion. So it's a property of matter that causes it to resist changes in its motion. We'll say in its state of motion. Right? So objects that are sitting still, they don't just start moving for no reason, right? And this is because of the concept of inertia. Something has to come along and make them move. And the bigger an object is, the more massive an object is, the more inertia it tends to have. Okay, so objects at rest will remain at rest unless acted upon by an outside force. The size of the force required to create motion in these cases is a direct consequence of the object's inertia, right? So the size of the force required to cause motion is related to the amount of inertia an object has, right? And consequently, inertia is directly related to the amount of mass an object has. So objects at rest will want to stay at rest, and objects in motion will want to remain in motion. It takes some kind of an outside force to change them, and the amount of the force is directly related to the amount of inertia, and i.e. the mass of the object. Okay, and again, we'll study inertia at a later date, but let's do a problem, let's do an example where Newton's first law is critical. So here's a good example. It's also a nice kind of slightly more challenging physics problem. Let's say we have a block of mass m. A block of mass m is placed on an inclined plane. Okay, a block of mass m is placed on an inclined plane. The block is at rest. The block is at rest. Now the question is, what is the maximum angle at which the block will remain at rest? So what is the maximum angle? What is the maximum angle at which the block will remain at rest? All right, so that's the question. So let's draw a picture here to kind of see what's going on. Maybe it's clear, but just in case it isn't, let's draw a picture. So I've got some kind of an incline here. All right, so like a right angle there. And there's some angle here which describes how steep this incline is. And now sitting on this incline, I have a block of mass m. Okay, I'll put an m on there. Now the question is, if I adjust this angle, right? If I adjust this angle, if I make it steeper, how steep can I make it before the block starts to slide? Right? How steep can I make the angle before the block starts to slide? How steep can I make the angle before the block starts to slide? All right. So let's do a free body problem, or a free body diagram, sorry. Let's draw up all the forces at work here. And so sometimes if you're doing a free body diagram, the angle at which the forces are operating may be twisted slightly, but let's just do a straightforward free body diagram just so we can see what's going on here. So I've got mg pulling the thing down, right? I've obviously got the normal force, which always acts perpendicular to the surface that the object is sitting on. So I got the normal force moving up like this. Let's leave these as vectors. And then I've got friction operating here as well, and friction is going to be operating perpendicular to the normal force. So this is static friction that we are facing here. Okay, and so we've got static friction sort of holding the block up, right? So if I were to put this on the picture, there's your mg, there's your normal force, and there's your static friction. Okay, so I've got these pieces here. So what we really need to do is we need to kind of think through what the question is really trying to get at. The first thing to notice here is, of course, Newton's first law is at work here. So Newton's first law is kind of the key to the problem. The net force on the block must be equal to 0, right? Now, as theta increases, and it must be equal to 0, right, because there's no motion, right? Specifically, we want to know how high can the angle be so that the block will remain at rest. So at a certain point, if the angle gets too high, then the force of gravity gets too strong and it overcomes the static friction force, is essentially what happens. So as theta increases, the force of static friction will increase. But it'll increase up to a threshold. Right? It'll increase up to a threshold, and we need to identify that threshold. Okay. All right, so let's start with gravity. Now, let's talk about the picture here a little bit more also. Right, so, oh, sorry, drew it wrong. Bad drawing. Let's talk about the picture here a little bit more. So I've got this block, right, and it's sitting on this incline. Now, because it's on an incline, the force of gravity, all of the weight of the object isn't pulling it down, right? Or isn't pulling it down the incline. Only some portion of the gravity is actually pulling it in this direction. The other portion is pulling it in this direction, right? So gravity is kind of like, you know, it's got its separate components. So the piece of the gravity component that we're really interested in is this piece, right? We're really interested in this piece. So we're interested in this piece of the gravitational force. And you could characterize this piece as the component of gravity acting parallel to the incline. So this is the component of gravity acting parallel to the incline. Okay. And so what is that component? Let's think about what that component would be. And you know, sometimes these can be a little challenging. I recommend you just practice this a lot. Like always, whenever you're given a problem, you have to break down these components and you've got things at odd angles. Be very careful when you do it, right? So technically what we're interested in is, so you've got gravity pulling the thing straight down, right? That's mg. But you've also got these different components. You've got the component going like this, and then you've got a component that's perpendicular to that, right? So this is mg, right? And the part we're interested in is this part, which I'm going to label A. And so then this is theta, isn't it? Right? This angle must be theta down there. And so we can figure out what A is. To find A, we need to recognize that the sine of theta is equal to A over mg, right? So theta's there, that would be the opposite over the hypotenuse. And so that means that A is equal to mg sine of theta. Okay, so the component of gravity acting parallel to the incline is this. So A is the component of gravity acting parallel to the incline. Right? That's the part that's actually going to make the thing slide. Right? This part here, that's not going to make it slide. Right? That's offset by the normal force, and so that's not the part that's going to make it slide. A is the part that's going to make it slide. This guy here. Okay, and we figured out that A can be written as the mass times g times the sine of theta. Okay, so that's the component acting parallel, right? And so therefore, this other component, this piece here, right, this guy here, that's going to be mg cos theta, right? So let me draw this in here. So here you've got your. Let me switch pages. I'm going to switch pages here. So here you've got your incline, right? And gravity's coming straight down, and here's theta, right? So this is the actual incline here. The block is up here, right? And so this is mg sine theta. This is mg cosine theta, and this is just mg, isn't it? Right, so sometimes the geometry here can be a little tricky, so just make sure that take your time and understand all these pieces. Okay, so mg cos theta, this piece here, that's the part of gravity that's kind of pulling the block against the surface, and so that piece is going to be offset by the normal force, right? So the normal force, basically, the magnitude of the normal force is just going to be m times the magnitude, or sorry, so it's going to be mg cos theta, isn't it? Okay, so that's the part that's balanced against the normal force. Right, so in order for the block to not slide, the static friction the static friction force is going to have to balance the gravitational force, right? That's the key here. So this part of it here has to be balanced by F of S, F sub S, right? The static friction. So what is that static friction force? Well, we saw that the static friction force is equal to mu, static coefficient of friction, and times the normal force, right? And then we know now that the normal force is basically this thing here, right? It's mg cos theta. So I've got mu sub s times mg cos theta. Right, so that's my static friction force. Okay, so in order for the block to not slide, this force must balance against the gravitational force that's acting parallel to the incline. Right, so that's this part. So what we need, in order for this to not slide, we need mg sine of theta to be less than or equal to mu sub s mg cos theta. Right? So this is the gravity component, and this is static friction. Right? So you got these two parts. So then the question would be, as theta changes, how does this inequality change? Right? Depending on what mu sub s is, this is going to, dial up. Now notice that the mass of the object doesn't even matter, right? You can cancel mass off of both sides, right? So let's go ahead and solve this for theta. So let's solve for theta. So what I would do is divide both sides by mg cos theta. So mg sine theta divided by mg cos theta is less than or equal to mu sub s mg cos theta divided by mg cos theta, right? And then of course the mg cos thetas all cancel out. The mg cancels out over here, so I get sine of theta over cosine of theta is less than or equal to mu sub s. Right, and then of course we know that sine theta over cos theta is tangent of theta. Okay, and so we get this. And so if you know something about tangent, you'll know that you'll know that the maximum theta is going to be equal to the tangent of the static friction coefficient. So if I take the inverse tangent of that, that's going to tell me the maximum theta that will be possible before sliding occurs. As soon as we go above this theta, whatever it happens to be, sliding will begin. Okay, so let's plug in a couple of values for mu sub s just to see what we get. Okay, so let's say we'll plug in two values just to see here. Let's say we've got mu sub s1 we'll set to 0.01, and this would be like slippery ice or something. So something really slippery. And then we'll also try mu sub s2 set to 0.8, and this would be like more like sandpaper. Not the roughest sandpaper, but like a rougher surface. I'll just put sandpaper, just so you know this is rough. Smooth and rough, smooth and rough. Right, and so theta of ice is equal to the inverse tangent of 0.01. All right, which we get 0.57 degrees. So about 1/2 of 1 degree is all that this scenario can support if we're dealing with something really slippery like ice. What about theta of sandpaper? Well, inverse tangent of 0.8. And when we plug all that in, you'll see we get 38 degrees. Right, and so 38 degrees, that's quite steep. That's more like this, isn't it? Ish. It's maybe a little less than that. Whereas the ice is like just the slightest inclinations. This is like all that you can handle with ice, and this is sandpaper. Right, so you can see how different that static coefficient is in practice, right? So as you crank up that mu, you get very, very different scenarios. Okay. All right, so that was a good example. The key takeaway from this section really is that Newton's first law tells us something about the forces that are at work for objects that are at rest, for objects that are at rest or for objects that are undergoing constant velocity, right? And specifically, it tells us that the sum of those forces is equal to 0, right? When you add them all together, if the object has no acceleration, then all of the forces must be canceling one another out. And that really is the key. And it'll come up in problems like this all the time. So just always have in the back of your mind, is there any acceleration? Does the physics problem have any acceleration in it whatsoever? If it does, then Newton's first law probably can't be used as easily. If there's no acceleration, well, it can still be used, but just not in this way. If there's no acceleration, then you know that the sum of all those forces must be equal to 0, and that's frequently a starting point for a lot of physics problems. All right, that will do it for this one. In our next lecture, we'll jump into Newton's second law, and we'll just keep building on these concepts. And so then finally the third law after that. And in each of these lectures, we're going to do a challenging physics problem that kind of incorporates the principle. So, all right, take care until next time.